What if we're not alone? Out there, beyond the faint glow of our solar system, worlds unlike anything we've ever imagined drift silently through the cosmos, some so eerily similar to Earth that scientists believe they could cradle life. For centuries, humanity has stared at the stars and wondered if other beings might be gazing back. And today, thanks to the relentless march of science, we're closer than ever to finding an answer. Picture this: over 5,000 exoplanets, planets orbiting distant stars, have already been discovered, each one a tantalizing clue in the greatest detective story of all time. But among them, a rare few stand out, worlds with the perfect recipe for life as we know it: liquid water, stable atmospheres, and just the right distance from their suns to make the impossible seem possible. Think about that for a moment. Our galaxy alone, the Milky Way, is home to hundreds of billions of stars, and around many of them, planets dance in delicate balance. Some are scorched wastelands, others frozen tombs, but tucked away in the cosmic expanse are places where conditions might mirror our own pale blue dot. Scientists call them Goldilocks planets, not too hot, not too cold, but just right, and the methods we use to find them are nothing short of miraculous. From measuring the faint dimming of starlight as a planet passes by to detecting the subtle wobble of a star tugged by an orbiting world, every discovery is a triumph of human ingenuity. But here's what really sends chills down your spine. If life exists on even one of these distant shores, it would change everything. The universe would go from a vast, empty stage to a thriving cosmic neighborhood. That's exactly why today's journey is so thrilling. We're about to explore 30 of the most promising exoplanets ever discovered, worlds where oceans might ripple under alien suns, where mountains could pierce skies of pink and orange, and where, just maybe, something stirs in the shadows. Some of these planets are so strange they defy imagination, with years that last mere days or skies lit by multiple suns. Others feel almost familiar, like Earth's long-lost twins. And while we may not have definitive proof of life yet, each of these worlds holds a secret, a story waiting to be uncovered. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The question isn't just, are we alone? It's, how soon until we meet the neighbors? Let's begin with our cosmic next-door neighbor, Proxima Centauri b. Just over 4 light-years away, this fascinating world orbits Proxima Centauri, the closest star to our Sun. And while that distance might still sound unimaginably vast in the grand scale of the universe, it's practically right next door. What makes this planet so special? For starters, it sits snugly in its star's habitable zone, that sweet spot where temperatures could allow liquid water to pool on the surface. And where there's water, there's potential for life as we know it. With a mass roughly 1.3 times that of Earth, Proxima Centauri b isn't just a distant curiosity. It's a world that feels eerily familiar, a rocky planet that could, in theory, cradle oceans, continents, and maybe even living organisms. But here's where things get complicated. Proxima Centauri isn't like our steady, reliable Sun. It's a red dwarf, a much smaller, cooler, and far more tempestuous star. These stars are known for their violent flares, eruptions of radiation that could strip away atmospheres and bathe nearby planets in deadly doses of ultraviolet and X-ray radiation. If Proxima Centauri b had an Earth-like atmosphere, it might have to fight hard to keep it. And then there's tidal locking, a phenomenon where one side of the planet always faces its star, locked in perpetual day, while the other half languishes in eternal night. This could create extremes of temperature, with scorching heat on one side and freezing cold on the other. Yet life is resilient. Some scientists speculate that if this world has a thick enough atmosphere, winds might circulate heat, creating a narrow band of milder conditions between the two extremes. Or perhaps beneath an icy crust, hidden oceans could thrive, shielded from the star's wrath. The possibilities are as tantalizing as they are uncertain. And that's what makes Proxima Centauri be so compelling. It forces us to ask not just whether life could exist there, but how it might adapt to conditions we've never seen on Earth. The answers could reshape everything we think we know about biology, survival, and our place in the cosmos. Now let's turn our gaze to a planetary system that reads like something straight out of science fiction: TRAPPIST-1. At its heart lies TRAPPIST-1e, a world so Earth-like in size and composition that it's become one of the most studied exoplanets in the hunt for alien life. Picture this: a star smaller and cooler than our Sun, hosting not just one or two, but 7 known planets, 3 of which sit perfectly within the habitable zone where liquid water could exist. And TRAPPIST-1e might just be the crown jewel of this extraordinary family. What makes this planet so intriguing? For starters, it's almost a mirror image of Earth in terms of size and density, suggesting a rocky surface with the potential for continents, valleys, and maybe even vast oceans. But here's where things get even more fascinating. TRAPPIST-1e could have a thick, protective atmosphere, something scientists are desperate to confirm. An atmosphere would mean the planet might hold onto heat, circulate air, and perhaps even shield life from the harsh radiation of its red dwarf star. And while these stars are notorious for their violent flares, TRAPPIST-1 has been surprisingly calm, offering a glimmer of hope that its planets haven't been stripped bare by stellar tantrums. Then there's tidal heating, a phenomenon where gravitational forces from the star stretch and squeeze the planet's interior, generating heat. On a world like TRAPPIST-1e, this could power volcanic activity, hydrothermal vents, or even subsurface oceans. And if there's one thing we've learned from Earth's extremophiles, it's that life thrives in the most unexpected places. Imagine a world where the ground itself hums with warmth, creating pockets of liquid water far beneath the surface, hidden from the star's fickle moods. But the real magic of TRAPPIST-1 isn't just one planet, it's the system itself. With 3 potentially habitable worlds orbiting the same star, the possibilities for life multiply. If one planet proves inhospitable, its neighbors might tell a different story. It's a cosmic laboratory, offering scientists a rare chance to study multiple Earth-like worlds at once. And in that symphony of orbits, TRAPPIST-1e stands out as a world that could rewrite the rules of what we consider a living planet. Every clue we uncover here doesn't just tell us about one distant world, it reshapes our understanding of life's potential everywhere. Kepler 186f isn't just another exoplanet. It's a milestone in our cosmic quest. This remarkable world holds the distinction of being the first Earth-sized planet ever discovered snugly within its star's habitable zone, a place where water could flow as freely as it does on our own planet. Picture a world about 10% larger than Earth, orbiting a red dwarf star 500 light-years away in the constellation Cygnus. At first glance, it seems like the perfect candidate for life, rocky, with just the right distance from its star to avoid being roasted or frozen. But the deeper we look, the more fascinating and puzzling this planet becomes. Red dwarfs like Kepler 186 are the universe's frugal energy savers, small, dim, and incredibly long-lived. While our Sun will shine for about 10 billion years, these stars can burn for trillions, offering a stable haven for life to evolve over mind-boggling timescales. But there's a catch. Planets orbiting so close to these faint stars often become tidally locked, with one hemisphere perpetually bathed in sunlight while the other is lost in eternal darkness. Imagine a world where the sun never sets or never rises. On the day side, temperatures might soar to levels that could sustain liquid water, even lush vegetation, while the night side could be a frozen wasteland. Yet life, if it exists here, might find a way. In the twilight zone between these extremes, a narrow band where the scorching day meets the icy night conditions could be surprisingly hospitable. Winds might carry warmth from the sunlit side, moderating temperatures and creating pockets where liquid water could persist. Or perhaps underground aquifers or thick ice sheets could shelter microbial life, much like the extremophiles hidden beneath Earth's deserts or polar caps. There's even speculation that if Kepler 186f has a dense atmosphere, heat could circulate more evenly, softening the harsh divide between day and night. What truly sets this planet apart, though, is what it taught us about possibility. Before its discovery in 2014, we weren't sure Earth-sized worlds could exist in habitable zones at all. Kepler 186f proved they could, opening the floodgates for countless similar discoveries. It's a reminder that the universe loves variety, offering not just copies of our own planet, but entirely new blueprints for how life might take hold. Whether this particular world is barren or teeming, one thing's certain: it redefined what we thought was possible, and in the search for life beyond Earth, that changes everything. LHS 1140b isn't just another habitable zone planet. It's a cosmic heavyweight with secrets that could rewrite the rules for life beyond Earth. Orbiting a quiet red dwarf star about 49 light-years away, this super-Earth is roughly 1.7 times the size of our own world, but with nearly 7 times the mass. That extraordinary density suggests something extraordinary beneath its surface. A vast, iron-rich core, possibly wrapped in a rocky mantle and crowned with something even more precious, a thick, life-sustaining atmosphere. What makes this world so special? Unlike the violent flares of Proxima Centauri or other temperamental red dwarfs, LHS 1140 is remarkably calm. Its steady glow means planets in its orbit aren't constantly battered by bursts of lethal radiation. And for LHS 1140b, that stability could be the key to preserving an atmosphere, a protective blanket that might trap heat, maintain pressure, and most crucially, keep water liquid. Even though the star itself is dim, barely 20% the size of our Sun, the planet's potential atmospheric density could act like an insulating layer, redistributing warmth enough to prevent its oceans from freezing solid. Then there's the tantalizing possibility of a global ocean. Given its size and composition, this planet might not just have scattered lakes or subsurface reservoirs. It could be a true water world with a single, unbroken ocean stretching across its entire surface beneath a hazy, humid sky. Imagine standing on an alien shore, looking out at endless waves under a dim, reddish sun. But here's the twist: that same crushing atmosphere might also create a pressure cooker effect, turning the surface into a steamy, superheated realm where water exists in a strange, slushy state between liquid and gas. Yet life, if it's there, might not need a surface at all. Some models suggest LHS 1140b could have a cold trap, a layer in its atmosphere where temperatures and pressures align perfectly to form a suspended ocean of water droplets, a permanent, planet-wide mist where microbial life could float indefinitely. Or perhaps, like Jupiter's moon Europa, it hides a subsurface ocean shielded from the faint star's light by miles of ice, warmed from below by geothermal vents. This is the beauty of exoplanet science. Every new discovery forces us to rethink what's possible. LHS 1140b doesn't just challenge our assumptions about habitable zones, it expands them. A planet this massive, this dense, shouldn't be Earth-like at all. And yet, against all odds, it might be one of our best bets for finding life. Because if biology can thrive here in this alien twilight, it means the universe is far more inventive and far more hospitable than we ever dared to dream. Among the ocean of exoplanets discovered, Kepler 442b stands out as a rare gem, a world that doesn't just hint at habitability, but practically ticks every box on the cosmic checklist. Orbiting a K-type star over 1100 light-years away, this planet has something most habitable zone worlds lack: stability. Unlike the fiery tantrums of red dwarfs, K-type stars are calmer, older, and more predictable, bathing their planets in a steady golden glow for billions of years. And that consistency could make all the difference for life taking root. with a radius just 1.3 times Earth's, Kepler 442b is strikingly similar in size to our own planet. But here's what really sparks excitement. Its position in the habitable zone is nearly ideal. While some planets teeter on the inner or outer edges of this region, leaving them either scorched or frozen, this world orbits at a distance where temperatures could allow liquid water to exist across vast stretches of its surface. And with a star that emits light at wavelengths plants on Earth thrive under, something astonishing becomes possible: alien photosynthesis. Imagine forests of deep violet or burgundy vegetation stretching across rolling hills, their leaves adapted to capture the slightly redder light of a K-type star. On Earth, plants use chlorophyll to absorb blue and red light, reflecting green. But under Kepler 442b's sun, evolution might have crafted entirely new pigments optimized for a different spectrum. This isn't just speculation. Studies suggest the planet receives enough photosynthetically active radiation to sustain complex plant life, something even promising worlds like Proxima Centauri b struggle with due to their star's faintness. Yet the advantages don't stop there. K-type stars have lifespans 2 to 3 times longer than our Sun, offering a stable environment for life to evolve over tens of billions of years. That's an unimaginable stretch of time, long enough for civilizations to rise, fall, and rise again, or for life to develop complexities we can't even fathom. And with less ultraviolet radiation than red dwarfs, the atmosphere here wouldn't face the same relentless erosion, increasing the chances it's still intact after eons. Of course, mysteries remain. Does Kepler 442b spin on its axis, creating day and night cycles, or is it tidally locked like many red dwarf planets? Does it have a magnetic field strong enough to deflect stellar winds? These unanswered questions keep scientists glued to their telescopes. But one thing's certain: in a universe where most habitable zone planets orbit temperamental red dwarfs, this world is a sanctuary. It's a reminder that Earth might not be the gold standard for life, just one variation in a galaxy full of possibilities. And if we ever find proof of a living, breathing ecosystem here, it won't just change biology textbooks. It'll redefine our place in the cosmos. GJ 357d isn't just another exoplanet, it's a cosmic enigma, a super-Earth that defies expectations. Orbiting a quiet M-type star just 31 light-years away, this world is close enough to spark excitement yet distant enough to keep its secrets locked tight. What sets it apart? For starters, it's roughly 6 times the mass of Earth, placing it in that intriguing category of planets we call super-Earths. Not quite small enough to be rocky like our own, but not so massive that it becomes a gaseous mini-Neptune. This delicate balance means GJ 357d could have everything life needs: a solid surface, a stable climate, and most tantalizing of all, a thick, insulating atmosphere. The planet's orbit is a masterpiece of cosmic timing. It circles its dim red dwarf star every 55.7 days, placing it squarely in the habitable zone, the region where temperatures might allow liquid water to exist. But here's the twist: because the star is so faint, GJ 357d huddles much closer than Earth does to the Sun. If you stood on its surface, the star would loom large in the sky, casting a dim, reddish glow over a landscape that could range from icy tundras to steam-shrouded wetlands, depending on how its atmosphere distributes heat. And that atmosphere is the key to everything. Scientists suspect this planet could be shrouded in a dense blanket of gases, possibly rich in hydrogen or even carbon dioxide. A thick atmosphere would act like a planetary thermostat, trapping just enough heat to compensate for the star's faint light. It might also shield the surface from harmful radiation, creating pockets where life could cling to existence. But there's a catch. GJ 357d is tidally locked, with one side perpetually baked in starlight and the other plunged into eternal night. Without an atmosphere, this would create brutal extremes, yet with one, winds could ferry warmth from the day side to the night, weaving a narrow ribbon of habitability along the twilight zone. The real challenge peering through the veil, at 31 light-years away, GJ 357d is too distant for current telescopes to analyze its atmosphere directly. But upcoming missions like the James Webb Space Telescope could change that, searching for the chemical fingerprints of water vapor, methane, or even oxygen. Every flicker of light from this distant world carries a story, one that might rewrite our understanding of where life can thrive. And if GJ 357d does hold an atmosphere, it wouldn't just be a scientific breakthrough. It would be a beacon proving that even in the quiet corners of the galaxy, worlds like ours might be waiting. TOI 700d isn't just another exoplanet, it's a triumph of precision and persistence. Discovered by NASA, a transiting exoplanet survey satellite, or TESS, this world made history as the first Earth-sized planet found in the habitable zone of a quiet M-dwarf star. Picture a planet almost exactly our size, orbiting a small, cool star just over 100 light-years away in the constellation Dorado. What sets TOI 700d apart isn't just its size or location. It's the extraordinary way scientists pieced together its story, transforming faint flickers of starlight into a vivid portrait of a world that could be cloaked in endless oceans. The star it orbits, TOI 700, is the kind of cosmic neighbor you'd want for a habitable planet, stable, gentle, and remarkably calm. Unlike the violent flares of many red dwarfs, this star emits little radiation, offering its planets a rare gift, a chance to hold onto their atmospheres for billions of years. And TOI 700d takes full advantage. Nestled in the habitable zone, it completes an orbit every 37 days, close enough to its dim star to stay warm but not so close that it's scorched. But here's the catch: like many planets around such stars, it's tidally locked. One side basks in perpetual daylight, the other shrouded in eternal night. Yet this tidal lock might not be the death sentence for habitability it once seemed. Advanced climate models reveal something astonishing. TOI 700d could be a true water world, its entire surface swallowed by a vast planet-spanning ocean. On the day side, heat from the star would keep the water liquid, while powerful currents driven by temperature differences could carry warmth to the night side, preventing it from freezing solid. Imagine standing on an alien shore, waves crashing under a dim, reddish sun, while storms rage along the twilight zone where day meets night. But the real magic lies in the atmosphere. Simulations suggest this planet could have a thick carbon dioxide-rich blanket, similar to early Mars but with a crucial difference: enough pressure to keep water liquid. Add in the possibility of clouds reflecting excess heat, and you've got a recipe for a stable, if alien, climate. It's a world where life wouldn't need continents to thrive, just deep, briny waters and time. TOI 700d forces us to rethink what makes a planet livable. It's not just about being Earth's twin. It's about the endless creativity of nature, crafting environments we're only beginning to imagine. And with TESS still scanning the skies, this discovery is just the beginning. A glimpse into a future where ocean worlds might be the rule, not the exception. K2-18b isn't just another exoplanet, it's a cosmic chimera, a world that blurs the line between what we know and what we dare to imagine. Discovered orbiting a dim red dwarf star 124 light-years away, this mysterious planet belongs to an entirely new category scientists call Hycean worlds, a term merging hydrogen and ocean. Picture a planet larger than Earth but smaller than Neptune, wrapped in a thick, hydrogen-rich atmosphere, with surface conditions so extreme they defy earthly logic. Yet beneath that crushing gaseous veil, something extraordinary might exist. Vast, globe-spanning oceans kept liquid not by sunlight, but by the planet's own internal heat and atmospheric pressure. What makes this discovery so groundbreaking? In 2019, astronomers studying K2-18b did something unprecedented. they detected water vapor in its atmosphere. Not just traces, but significant amounts swirling in the hydrogen-rich air. For a Hycean world, that's like finding smoke near a fire. Where there's water vapor, there could be liquid water. And where there's liquid water, there's potential for life. But this isn't the familiar blue marble we know. Hycean planets operate by different rules. Their oceans might not rest on a rocky seafloor, but dissolve into a soupy, supercritical fluid where liquid and gas phases blur. Temperatures could soar to hundreds of degrees, yet the immense pressure prevents the water from boiling away. The implications for life are staggering. On Earth, we've found microbes thriving in scalding hydrothermal vents, acidic pools, even the vacuum of space. If extremophiles can survive here, why not in the deep, dark oceans of K2-18b? Some scientists speculate that beneath its hydrogen shroud, organic molecules could form in the turbulent boundary where atmosphere meets ocean, fueled by chemical energy rather than sunlight. Imagine a world where life doesn't depend on photosynthesis, but on chemosynthesis, a place where alien microbes harvest energy from the reactions between water and hydrogen, creating ecosystems entirely divorced from the rhythms of day and night. Yet mysteries linger. That same thick atmosphere could be a double-edged sword. While it traps heat and maintains pressure, it might also block vital nutrients from reaching the depths or create layers so dense they crush complex chemistry. And without a magnetic field, stellar radiation could strip away the atmosphere over time, leaving the oceans exposed to the void. But here's the most thrilling part: we're on the verge of finding out. The James Webb Space Telescope has already set its sights on K2-18b, probing its atmosphere for biosignatures molecules like dimethyl sulfide, which on Earth is only produced by living organisms. This isn't just about one planet, it's about rewriting the playbook for habitability. If life can thrive in the crushing depths of a Hycean world, it means the universe might be far more inventive and far more crowded than we ever dreamed. K2-18b isn't just a scientific curiosity. It's a key unlocking doors to realms we're only beginning to understand, and behind those doors something might be waiting. Teegarden star B isn't just another exoplanet, it's a cosmic relic, a world orbiting one of the oldest stars in our galactic neighborhood. This quiet red dwarf, barely 9% the mass of our Sun, has been burning faintly for at least 8 billion years, far longer than our solar system has even existed. And circling it is a planet that defies expectations. Teegarden star B, with a mass almost identical to Earth's, nestled perfectly in the star's habitable zone. But don't let its familiar size fool you. This is a world where the rules of habitability get rewritten. What makes this planet so extraordinary? First, consider its star. Teegarden star is so dim it wasn't even discovered until 2003, despite being just 12 light-years away. It emits less than 1% of the Sun's visible light, casting its planets in a perpetual twilight. Yet Teegarden star B might not be the frozen wasteland you'd expect. Thanks to a phenomenon called tidal heating, the planet could be warmed from within. Gravitational forces from its star continuously stretch and compress the planet's core, generating internal heat that might keep subsurface oceans liquid for eons. Imagine a world where life thrives not under the glow of sunlight, but powered by the slow, steady heartbeat of planetary friction. Then there's the atmosphere, or what it could be. Ultra-cool red dwarfs like Teegarden star emit far less ultraviolet radiation than their hotter counterparts, meaning any atmosphere here wouldn't face the same relentless erosion as planets orbiting flare-prone stars. If this world has a dense blanket of greenhouse gases like carbon dioxide or methane, it could trap what little heat the star provides, creating a stable, if chilly, surface environment. Picture sprawling tundras under a dull crimson sky, where hardy microbes or even complex organisms have adapted to the eternal gloom. But here's the most tantalizing possibility: time. 8 billion years is more than double Earth's age. That's an almost unimaginable span for life to emerge, evolve, and perhaps even reach intelligence. If biology took hold here, it's had epochs to experiment with forms and strategies we can't begin to predict. While Earth's evolutionary clock started relatively recently, Teegarden star B has been ticking since the universe was half its current age. Of course, mysteries linger. Is the planet tidally locked with one side forever facing the star? Does it have a magnetic field to shield against cosmic rays? These unanswered questions make Teegarden star B more than just a scientific curiosity. It's a test case for life's tenacity. Because if biology can flourish here in the faint glow of an ancient star, it means the cosmos might be humming with life in places we've barely begun to search. And that changes everything. Wolf 1061c isn't just another distant world, it's practically in our cosmic backyard. At just 14 light-years away, this intriguing exoplanet is one of the closest potentially habitable worlds we've ever discovered. Picture a planet orbiting Wolf 1061, a quiet red dwarf star faint enough to be invisible to the naked eye from Earth, yet close enough that future telescopes might one day glimpse its atmosphere in astonishing detail. But proximity isn't the only reason scientists are captivated. This super-Earth, weighing in at nearly 4 times our planet's mass, sits squarely in its star's habitable zone, that Goldilocks region where water could pool on the surface. Yet Wolf 1061c is no tranquil oasis. What makes this world so fascinating and challenging for potential life is its elliptical orbit, a stretched-out path around its star that creates wild swings in temperature. Imagine a year where seasons aren't gentle transitions but violent upheavals. As the planet swings closer to its star, surface temperatures could skyrocket, boiling away shallow seas or thawing frozen deserts. Then, as it retreats to the orbit's far side, bitter cold reclaims the landscape, locking water back into ice. These extreme fluctuations would test the limits of any ecosystem, forcing life to adapt to conditions that shift dramatically over mere months. But here's where nature might offer a surprising solution. A thick atmosphere could act as a planetary shock absorber, redistributing heat during those scorching close approaches and trapping warmth during the frigid stretches. Alternatively, tidal forces from the star might keep the planet's interior churning with volcanic activity, fueling hydrothermal vents that create stable oases of warmth beneath icy surfaces. And let's not forget the possibility of tidal locking, where one side of the planet always faces the star, creating a permanent day zone, a twilight ring, and a frozen far side. In that scenario, life might cluster along the terminator line, where temperatures could balance in a narrow, livable band. The real significance of Wolf 1061c lies in what it teaches us about planetary diversity. Most habitable zone planets we've found orbit in near-circular paths, but this world proves that stability isn't the only path to potential habitability. Extreme environments push us to reconsider life's boundaries, reminding us that biology on other worlds might flourish in ways we've never imagined. With upcoming telescopes poised to study its atmosphere, this nearby enigma could become the ultimate test case. Does life adapt to the chaos, or does it need calm to take root? The answer might redefine our search for cosmic company. HD 40307g isn't just another exoplanet, it's a cosmic rarity, a world that dances to its own rhythm. Orbiting a K-type star 44 light-years away in the constellation Pictor, this super-Earth breaks the mold of what we expect from habitable zone planets. With a mass at least 7 times greater than Earth's, it's hefty enough to hold onto a thick atmosphere, yet not so massive that it becomes a gaseous mini-Neptune. But what really sets this world apart isn't just its size, it's the way it moves. Unlike the tidally locked worlds clinging to red dwarfs, HD 40307g spins freely, rotating on its axis as it circles its star in a 200-day orbit. That means something extraordinary: sunrises and sunsets, real Earth-like days and nights, Imagine standing on the surface of this alien world, your sky washed in the golden glow of a K-type star slightly cooler and redder than our sun would change as the planet turns. Mountains on the horizon might catch the first light of dawn, while vast oceans, if they exist, could shimmer under the midday sun. And because of that rotation, heat wouldn't be trapped on one side like so many habitable zone planets. Instead, winds could sweep across continents, balancing temperatures and creating climates as diverse as Earth's own. Deserts, forests, ice caps all might coexist on a single world, each region offering a different stage for life's drama. But here's where the story gets even more compelling. K-type stars like HD 40307's Sun are often called Goldilocks stars for good reason. They're not just stable, they're practically ideal for life. Less active than red dwarfs, they don't bombard their planets with deadly flares, yet they live far longer than sun-like stars, burning steadily for tens of billions of years. That's an eternity for life to emerge, evolve, and perhaps even reach for the stars. The planet's elongated orbit adds another layer of intrigue. As HD 40307G swings closer to its star, temperatures might rise, triggering seasonal changes unlike anything on Earth. Oceans could swell with meltwater, while equatorial regions become lush with rain. Then, as it retreats, winter might descend, locking water back into ice at the poles. These cycles wouldn't just shape the climate, they'd test life's adaptability, potentially driving evolution toward resilience and complexity. What truly captivates scientists, though, is the atmosphere. A planet this massive likely held onto hydrogen and helium early in its life, but stellar winds may have stripped away the lighter gases, leaving behind a dense shroud of nitrogen, carbon dioxide, or even oxygen. If so, the stage could be set for something astonishing. With the right mix of gases, HD 40307G might not just be habitable, it might be inhabited. And with next-generation telescopes set to study its atmosphere in the coming decades, we could soon have our first clues. This isn't just a planet, it's a masterclass in cosmic diversity, proving that habitability comes in endless forms. Not too hot, not too cold, not tidally locked, not barren. HD 40307G is a world that dares us to dream bigger. Because if life thrives here, under a golden sun and sweeping skies, it means the universe might be far more vibrant, far more varied than we ever imagined. Kepler 62f doesn't just orbit in the habitable zone, it redefines it. Picture a world slightly larger than Earth, spinning around a star strikingly similar to our Sun, but older and wiser. Located about 1,200 light-years away in the constellation Lyra, this exoplanet is part of a system that reads like a cosmic mirror of our own, with not one but 5 known planets. But Kepler 62f stands out as the crown jewel, orbiting its star every 267 days in a region where liquid water could exist in abundance. What makes this planet so remarkable isn't just its placement, it's the tantalizing possibility that its entire surface might be an unbroken ocean, a water world with no land in sight. The similarities to Earth are uncanny. With a radius just 1.4 times that of our planet, Kepler 62f falls squarely into the category of rocky super-Earths. Its host star, a K-type slightly cooler and smaller than the Sun, bathes it in a gentle golden light, offering stability rare among the flare-prone red dwarfs that dominate the exoplanet catalogue. But here's where the mystery deepens. Despite years of observation, we still don't know if this planet has an atmosphere. Detecting atmospheres around distant worlds is like trying to study a fogged-up window from miles away, especially when the planet doesn't transit or pass directly in front of its star from our vantage point. Without that telltale dimming of starlight, scientists rely on indirect methods, piecing together clues from the faintest whispers of light. Yet the hints are too compelling to ignore. Climate models suggest that even a thin atmosphere, rich in carbon dioxide, could trap enough heat to keep Kepler-62f's potential oceans liquid. Add clouds into the mix and the planet's climate might stabilize further, with water vapor cycling between ocean and sky in an endless, life-sustaining loop. But there's a catch. If this is a true water world with no landmass to break the surface, essential nutrients might be locked away in the depths. On Earth, continents erode, washing minerals into the seas, a process that might not exist here. Life, if it exists, would need another way to access the building blocks of biology. Then there's the question of time. Kepler-62f star is billions of years older than the Sun. If life arose here, it's had an unimaginable head start. Imagine civilizations that could have risen and fallen epochs before the first fish crawled onto Earth's shores. Or perhaps in the absence of land, evolution took a different path entirely. Think intelligent creatures navigating endless oceans, their cultures shaped by the rhythms of tides and currents. The beauty of Kepler-62f lies in its contradictions. It's familiar enough to spark recognition, yet alien enough to stretch our imagination. It challenges us to reconsider what makes a planet habitable, not just the presence of water, but the delicate interplay of atmosphere, chemistry, and time. And as telescopes grow more powerful, this distant world may finally reveal its secrets, showing us that Earth is just one variation in a universe teeming with possibilities. GJ667cc isn't just another habitable zone planet. It's a cosmic tightrope walker, balancing gracefully in a stellar dance most worlds would find chaotic. This super-Earth, with a mass nearly 4 times greater than our home planet, orbits the smallest member of a triple star system just 22 light-years away. Picture that for a moment, a world where the sky could host not 1, not 2, but 3 suns, each casting its own light and shadow across alien landscapes. Yet against all odds, GJ667cc sits snugly in its star's habitable zone, a testament to nature's ability to forge stability from celestial complexity. What makes this planet so extraordinary is its star GJ667c, a red dwarf so faint it was initially overlooked in a system dominated by 2 brighter orange dwarfs. While those larger stars orbit each other closely, GJ667c swings around them at a much greater distance, creating a gravitational safe zone where its planets can thrive. And GJ667cc, orbiting this quiet red dwarf every 28 days, reaps the benefits. Despite the system's triple star drama, this planet's path is remarkably steady, shielded from the gravitational tug of war that might otherwise fling it into the void. But the real marvel lies in the climate. With 3 stars in its sky, you'd expect GJ667cc to endure wild temperature swings, yet simulations suggest otherwise. The 2 outer stars, though bright, are distant enough that their combined light adds only a fraction of the warmth the planet receives from its primary red dwarf. Think of them as cosmic nightlights, casting a soft glow rather than scorching heat. Meanwhile, the planet's thick atmosphere, likely retained thanks to its super-Earth mass, could act as a buffer, smoothing out any residual fluctuations. Imagine a world where twilight is a permanent spectacle, with multiple suns painting the horizon in hues of amber and gold, while the air itself wraps the surface in a temperate embrace. Life here, if it exists, would need to adapt to an unusual rhythm. The primary red dwarf provides most of the energy, but the occasional passes of the other stars could create subtle seasons, periods where the ambient light brightens just enough to trigger blooms of alien vegetation. And with such a massive planet, gravity would be stronger, potentially leading to denser, more robust life forms capable of thriving under these unique conditions. GJ667cc challenges our assumptions about habitability. It proves that even in the most dynamic systems, nature finds a way. If life can take root here amid the gentle pull of 3 suns, it means the universe might be far more inventive and far more hospitable than we ever dared to dream. Kepler 452b isn't just another exoplanet. It's the closest thing we've found to Earth's long-lost twin. Nicknamed Earth's cousin, this world orbits a star almost identical to our Sun, a G-type main sequence star at nearly the same distance Earth does. Picture a planet just 60% larger than our own, bathed in sunlight almost indistinguishable from ours, with a year lasting 385 days, only 20 days longer than Earth. At first glance, it feels like coming home, but the deeper you look, the more hauntingly beautiful this world becomes. What sets Kepler 452b apart isn't just its similarities, it's the time it's had to evolve. This planet is ancient. Its star, Kepler 452, is 1.5 billion years older than our Sun. That means if life took root here, it's had an extra 1.5 billion years to grow, adapt, and perhaps even reach heights we can't fathom. Imagine civilizations that could have risen and fallen before Earth's first single-celled organisms even appeared. Forests might have climbed toward alien skies for eons, species could have come and gone in waves, and intelligence might have emerged in forms we'd struggle to recognize. Yet this planet's age is also its greatest challenge. Older stars grow hotter as they age, and Kepler 452 has likely brightened by about 10% since its planet formed. That subtle increase could have triggered a runaway greenhouse effect, slowly boiling away oceans and leaving behind a parched, Venus-like world. Or perhaps the planet's atmosphere thickened over time, trapping enough heat to compensate for the star's growing intensity, creating a stable, if steamy, paradise. The difference between those two fates might come down to something as delicate as volcanic activity. Whether the planet's geology recycled enough carbon dioxide to maintain equilibrium or let it spiral out of control. Then there's the star itself. Unlike the volatile red dwarfs that dominate the exoplanet catalog, Kepler 452 is reassuringly familiar. Sun-like stars offer something rare in the cosmos: consistency. No violent flares stripping away atmospheres, no tidal locking forcing one side into perpetual day. Just the steady rhythm of sunlight and seasons, a cadence life on Earth has depended on for billions of years. If Kepler 452b has managed to hold onto its water, it could be a living testament to the endurance of biology, a world where evolution has had more time to experiment than we can comprehend. The real tragedy, distance. At 1,400 light-years away, we'll never visit this world in person. But with next-generation telescopes, we might one day glimpse its atmosphere, searching for the telltale signs of oxygen, methane, or even industrial pollution. Because if Kepler 452b teaches us anything, it's that Earth isn't special, it's just early. The universe has been crafting Earth-like worlds for far longer than we've existed, and some of them might have stories to tell that dwarf our own. Ross 128b offers something rare in the cosmic hunt for habitable worlds: a peaceful home. Orbiting one of the quietest red dwarfs known, this exoplanet sidesteps the greatest threat to life around these dim stars: violent radiation. While most red dwarfs erupt with flares capable of stripping atmospheres and sterilizing surfaces, Ross 128 simmers like a forgotten ember, its steady glow offering a gentler rhythm to the planet circling just 7.4 million miles away. That proximity would be deadly around a star like our Sun, but here it places Ross 128b squarely in the habitable zone, where temperatures might allow liquid water to pool under a perpetual twilight sky. What makes this planet truly remarkable is its balance. With a mass only 1.3 times Earth's, it's almost certainly rocky, a world where mountains could rise above valleys and oceans might carve coastlines. Yet its orbit completed in just under 10 days defies expectations. So close to its star, you'd expect a tidal lock with one face scorched and the other frozen. But simulations suggest Ross 128b might rotate just enough to avoid this fate, offering something closer to a real day-night cycle. Imagine a world where the Sun, a deep crimson orb 3 times larger in the sky than our own, drifts lazily overhead, casting long shadows across a landscape that slowly turns beneath it. The possibilities for atmosphere here are tantalizing. Red dwarfs like Ross 128 emit far less ultraviolet light than younger, hotter stars, reducing the erosion that dooms many exoplanet atmospheres. Combine that with the planet's Earth-like gravity, and you've got a recipe for an airy shroud thick enough to trap heat, distribute warmth, and shield the surface from cosmic rays. Climate models paint intriguing scenarios. Some suggest a misty world with high humidity and moderate temperatures, while others hint at cooler, drier conditions where life might cluster around geothermal hotspots. But the real gift of Ross 128b is time. At 11 light-years away, it's one of our closest potentially habitable neighbors, close enough that future telescopes could study its atmosphere in unprecedented detail. And with a host star expected to burn for trillions of years, this planet isn't just a candidate for life today, it's a sanctuary that could outlast the Milky Way itself. Whether its surface holds barren rock or thriving ecosystems, Ross 128b stands as a quiet testament to the universe's patience, a world where stability might be the rarest ingredient of all. HD 85512b isn't just another world in the habitable zone, it's a masterclass in atmospheric alchemy. Orbiting a quiet K-type star 36 light-years away, this super-Earth packs 2.6 times the mass of our planet into a globe that might be cloaked in swirling clouds and endless oceans. But what really sets this world apart isn't just its size or location. It's the delicate balance of conditions that could transform it from a barren rock into a living paradise. Picture a star slightly cooler and smaller than our Sun, casting a soft golden glow across a planet completing its orbit every 58 days. That tight trajectory would be deadly around a hotter star, but here it nestles HD 85512b comfortably in the habitable zone's sweet spot. Early climate models revealed something astonishing. If this planet has an Earth-like atmosphere, surface temperatures could average a balmy 30 degrees Celsius, perfect for liquid water. But add just a few more clouds and something magical happens. Those floating veils of water vapor could reflect enough sunlight to prevent overheating, creating a self-regulating thermostat that keeps the climate stable for eons. The real intrigue lies in the atmosphere's composition. For water to exist here, the air must be thicker than Earth's, rich with greenhouse gases like carbon dioxide. Too thin and the planet's water would freeze, too dense and it might spiral into a runaway greenhouse effect like Venus. But Goldilocks scenarios aren't just possible, they're likely. K-type stars like HD 85512's Sun emit less ultraviolet radiation than their hotter counterparts, giving atmospheres a fighting chance to persist. And with the planet's stronger gravity, gases that would escape Earth's grip might linger here, weaving a protective shroud. Then there's the wild card, tides. Unlike the locked planets orbiting red dwarfs, HD 85512b might rotate freely, allowing day-night cycles that distribute heat evenly. Imagine coastlines where waves lap under a peach-colored sky, where clouds drift across continents as alien seasons come and go. It's a vision of habitability that feels almost familiar, until you remember this world's staggering density. A surface gravity 1.4 times Earth's would turn every step into a labor, every mountain into a crushing colossus. Life here would need strength to match, or perhaps ingenuity to navigate oceans so heavy they feel like syrup. The genius of HD 85512b is how it challenges our assumptions. Not all habitable worlds are Earth clones. Some are denser, cloudier, bathed in stranger light. And if this planet proves one thing, it's that life's recipe might be more flexible than we ever dreamed. Water, air, and time. The universe mixes them in endless ways, and sometimes, against all odds, they yield something extraordinary. Kepler 1638b isn't just another exoplanet, it's a cosmic doppelganger, a world so eerily similar to Earth in size and orbit that it blurs the line between science and science fiction. Picture a planet with a radius just 1.02 times that of our own, a near-perfect match, circling a star almost indistinguishable from the Sun. Located about 3,000 light-years away in the constellation Cygnus, this world completes an orbit every 259 days, placing it squarely in its star's habitable zone, that delicate region where liquid water could pool on the surface. If you squint, it's easy to imagine Kepler 1638b as Earth's mirror image, with continents, oceans, and skies that might feel hauntingly familiar. Yet appearances can be deceiving. The star it orbits, Kepler 1638, is a G-type main sequence star, just like our Sun, but slightly older and quieter. That stability is a gift. Unlike the flare-prone red dwarfs that dominate the exoplanet catalog, this star offers its planets a steady, gentle light, free from the violent outbursts that could strip away atmospheres or bathe surfaces in lethal radiation. But here's the catch: 3,000 light-years is an unimaginable gulf. At that distance, even our most powerful telescopes struggle to discern whether this planet has an atmosphere, let alone what gases it might contain. Detecting an atmosphere around a distant world is like trying to study a candle's flame from across a foggy battlefield. The light is faint, the interference overwhelming. Without that critical data, we're left with tantalizing possibilities. If Kepler 1638b has a thick atmosphere rich in nitrogen and carbon dioxide, it could trap enough heat to maintain temperate conditions even as far out as it orbits. But if its air is thin or long gone, the planet might be a frozen desert, its water locked beneath ice or evaporated into space. The difference between those two fates could come down to something as simple as volcanic activity, whether the planet's interior still churns, recycling gases and replenishing the sky. What makes this world so compelling isn't just its Earth-like resume, it's the questions it forces us to confront. How many of these seemingly habitable planets are truly Earth's twins, and how many are barren impersonators? With current technology, we may never know for sure, but upcoming instruments like the Habitable Worlds Observatory, now in planning, could change that. Designed to directly image exoplanets and analyze their atmospheres, it might one day reveal whether Kepler 1638b's skies hold water vapor, oxygen, or even the chemical signatures of life. Until then, this world remains a masterpiece of cosmic ambiguity, a reminder that in the search for life, the universe loves to keep us guessing. GJ1214b isn't just another exoplanet, it's a cosmic pressure cooker, shrouded in mysteries that defy even our most advanced telescopes. Located just 42 light-years away in the constellation Ophiuchus, this enigmatic world orbits so close to its dim red dwarf star that a full year lasts a mere 38 hours. But don't let its proximity fool you. What makes this planet extraordinary isn't its speed, but what might lie beneath its thick, swirling veil of clouds, a global ocean so vast it could make Earth's seas look like puddles. Scientists classify GJ1214b as a water world, a term that barely captures its strangeness. With a radius 2.7 times Earth's and nearly 7 times the mass, this planet's density suggests something radical. Up to 10% of its bulk could be water. Not the gentle lakes and rivers we know, but an ocean hundreds of miles deep, crushed under pressures so intense the water might exist in exotic forms like hot ice or supercritical fluid, where liquid and gas phases blur into one. Imagine an abyss where the very bottom isn't rock but a slushy mantle of high-pressure ice, forming a barrier between the ocean and a molten core. Then there's the atmosphere, a stifling blanket of hydrogen and helium, possibly laced with steam from the roiling ocean below. Early observations revealed GJ1214b's air to be eerily uniform, lacking the chemical fingerprints we'd expect if it were a mini Neptune with a gaseous exterior. Instead, the best explanation is a dense, water-rich haze, like a planetary sauna where sunlight struggles to penetrate the gloom. This shroud makes studying the surface nearly impossible. It's like trying to peer through fogged-up glass while standing in a thunderstorm. Yet the intrigue doesn't stop there. Some models suggest this world might be a Hycean planet, a new class of exoplanet with hydrogen-rich atmospheres overlying oceans. If true, GJ-1214b could host extremophiles in its depths, organisms adapted to thrive without sunlight, drawing energy from chemical reactions at hydrothermal vents or the ambient heat of the planet's interior. Or perhaps the ocean is sterile, its waters too hot and heavy for even the hardiest life forms. The frustration and the fascination lies in our inability to know for sure. Current telescopes can't pierce that soupy atmosphere to glimpse what lies beneath, but future instruments like the James Webb Space Telescope might detect subtle clues in the planet's infrared glow, hints of water vapor, methane, or even biosignatures floating high in the haze. Until then, GJ-1214b remains a paradox, a world that could be drowning in the very ingredient life needs, yet locked in conditions so extreme they rewrite the rules of habitability. It's a reminder that the universe doesn't care about our definitions it creates, and we're left to wonder. Kepler 1229b isn't just another frozen world, it's a paradox wrapped in ice, a planet where the surface might be locked in perpetual winter, while beneath the frozen crust, oceans could churn with volcanic warmth. Orbiting a quiet red dwarf star over 700 light-years away, this Earth-sized gem completes its orbit in 86 days, placing it squarely in the habitable zone. But unlike planets basking in the glow of sun-like stars, Kepler 1229b lives in twilight, its dim star providing just enough heat to tease the possibility of liquid water, if not on the surface, then perhaps deep below. The secret lies in tidal heating. Just as Jupiter's moon Europa hides an ocean under miles of ice, this exoplanet could be flexed and stretched by its star's gravity, generating internal heat through friction. Picture a world where the ground itself is alive with movement, where the rhythmic pull of the star creates enough warmth to keep vast reservoirs of water liquid beneath a frozen shell. These hidden seas wouldn't rely on sunlight to stay warm, they'd draw energy from the planet's own tortured geology, with hydrothermal vents belching minerals into the darkness. It's a scenario that excites astrobiologists because on Earth, life thrives in exactly these conditions, clustered around volcanic vents in the abyss. Then there's the atmosphere, or lack thereof. Many red dwarf planets lose their air to stellar winds, leaving them barren. But if Kepler 1229b has a thick ice layer, it could act as a shield, trapping gases beneath the surface that might seep out through cracks, creating temporary pockets of breathable air. Some models even suggest that under the right conditions, geothermal heat could melt sections of the ice, forming vast subglacial lakes akin to Antarctica's Lake Vostok, but on a planetary scale. What makes this world so compelling is its defiance. On paper, a planet orbiting this close to a dim star should be uninhabitable, too cold for liquid water, too airless for life. Yet physics offers loopholes, and Kepler 1229b exploits every one. It's a reminder that habitability isn't just about distance from a star, but about the ingenuity of nature, finding ways to nurture life in the unlikeliest places. And while we may never see its hidden oceans directly, their potential existence reshapes our understanding of where life could hide, not just on warm, Earth-like worlds, but in the frozen dark where heat rises from below and the real action happens out of sight. Lytton B isn't just another habitable zone planet, it's a celestial survivor, clinging to existence in the turbulent embrace of one of the most active red dwarfs known. Just 12 light-years away, practically next door in cosmic terms, this super-Earth weighs in at nearly 3 times our planet's mass, giving it the gravitational muscle to potentially hold onto something precious, an atmosphere. That's no small feat when your star is Lytton's star, a red dwarf notorious for its violent flares, capable of bombarding nearby planets with enough radiation to strip away atmospheres over time. Yet against all odds, Lighten B endures, locked in an orbit that takes just 18 days to complete, so close to its dim sun that the star would appear 3 times larger in its sky than ours does on Earth. What makes this world so compelling is its delicate balancing act. Nestled squarely in the habitable zone, Lighten B receives about 6% more stellar energy than Earth does, enough that with a thick atmosphere, surface temperatures could hover around 19 degrees Celsius. That's sweater weather by Earth standards, but potentially paradise for alien life forms. The catch, that same atmosphere would need to withstand relentless stellar storms. Some models suggest Lighten B might have a Venus-like shroud of carbon dioxide, dense enough to deflect radiation while trapping heat efficiently. Others propose a more exotic scenario, an oxygen-rich atmosphere generated not by life, but by the constant breakdown of water molecules in the upper air, split by stellar radiation into hydrogen and oxygen. Then there's the water question. With its super-Earth gravity, Lighten B could maintain liquid oceans even under extreme conditions. Tidal forces from its star might keep water churning beneath icy crusts, much like Jupiter's moon Europa. Or perhaps, if the atmosphere is thick enough, surface water could exist in sprawling, shallow seas, sheltered from the worst of the flares. The planet's mass also hints at another advantage: active geology. A larger, warmer core could drive plate tectonics, recycling carbon and stabilizing the climate over billions of years, a critical factor for long-term habitability. The most tantalizing possibility, Lighten B might not be alone. Its star hosts at least one other planet, Lighten C, a colder world orbiting farther out. This raises the staggering prospect of a multi-planet system where life could have hopped between worlds, spreading through meteorite debris or even deliberate panspermia. At 12 light-years, we're already developing telescopes capable of analyzing Lighten B's atmosphere. Within our lifetimes, we might spot the telltale shimmer of ocean glint or the spectral fingerprint of vegetation. For now, this turbulent world remains a paradox, a planet that by all rights should be sterile, yet holds every ingredient life might need to not just survive but thrive. Kepler 1652b might just be Earth's understated twin, a world so close in size to our own that stepping onto its surface could feel eerily familiar, if not for the crimson glow of its tempestuous red dwarf star. This exoplanet, discovered by the Kepler Space Telescope, is a mere 10% larger than Earth, placing it among the select few worlds that match our planet's dimensions almost exactly. But its true allure lies in its orbit, a delicate dance within the habitable zone of its star, where temperatures could allow water to flow freely. Yet this isn't the gentle, sunlit haven Earth enjoys. Kepler 1652b orbits so close to its dim star that a full year lasts just 38 days, a blistering pace that locks it in a gravitational embrace fraught with challenges. The star itself is the wild card. Red dwarfs like Kepler 1652 are notorious for their violent outbursts, erupting with flares that can unleash torrents of X-rays and ultraviolet radiation enough to scorch atmospheres and sterilize surfaces. For a planet hugging its star this tightly, survival becomes a high-stakes balancing act. But here's where the plot twists. Kepler 1652b might have a secret weapon. Geothermal activity. With a rocky composition similar to Earth's, this world could harbor a molten core, its interior churned by tidal forces from the star's relentless pull. Imagine underground reservoirs heated by volcanic vents, their warmth shielding microbial life from the deadly radiation above. Or perhaps tectonic activity recycles gases, replenishing the atmosphere faster than flares can strip it away. Then there's the tantalizing possibility of tidal locking. Like many planets orbiting red dwarfs, Kepler 1652b likely has one face permanently bathed in starlight while the other languishes in eternal night. But instead of rendering the planet lifeless, this extreme contrast might create a narrow band of twilight where temperatures hover in a sweet spot, neither scorching nor frozen, but just right. Winds could ferry warmth from the day side to the night, weaving a ribbon of habitability along the terminator line. And if the planet's atmosphere is thick enough, it might even distribute heat more evenly, softening the harsh divide. What makes Kepler 1652b so compelling isn't just its Earth-like resume, it's the reminder that habitability isn't a one-size-fits-all formula. This world forces us to reconsider where life could cling, thriving not despite the chaos but because of it. With every flare its star unleashes, with every tectonic shift beneath its surface, this planet writes its own rules. And as we peer deeper into its mysteries, we're left with a humbling thought. If life can endure here in the shadow of a tempestuous star, then the cosmos might be far more inventive and far more resilient than we ever imagined. TRAPPIST-1F isn't just another world in its star's habitable zone. It's a masterclass in celestial teamwork, orbiting as part of one of the most tightly packed planetary systems ever discovered. Picture this: 7 Earth-sized planets circling their dim red dwarf star in a delicate cosmic choreography, so close together that standing on TRAPPIST-1F's surface would reveal neighboring worlds hanging in the sky like oversized moons. But what truly sets this planet apart isn't just its crowded celestial neighborhood. It's the tantalizing possibility that beneath a thick, swirling atmosphere, an ocean might stretch across its entire surface, a shimmering blanket of liquid hiding secrets we can only dream of uncovering. Positioned as the 5th planet from its star, TRAPPIST-1F occupies the outer edge of the system's habitable zone, where the star's faint glow should leave it frozen solid. Yet climate models reveal a stunning loophole. If this world has an atmosphere rich in greenhouse gases, think carbon dioxide or even methane, it could trap just enough heat to keep water liquid. Not in scattered lakes or subsurface pockets, but as a planet-spanning ocean, unbroken by continents or land masses. The physics at play here is breathtaking, a delicate balance where the very air itself becomes a thermostat, holding warmth close to the surface despite the star's weak light. But the atmosphere's role doesn't stop at temperature control. Around red dwarfs like TRAPPIST-1, stellar winds and radiation can strip away air over time, leaving planets barren. TRAPPIST-1F's potential saving grace, its size. With a mass slightly less than Earth's, it might lack the gravity to hold onto lighter gases like hydrogen, but heavier molecules, carbon dioxide, nitrogen, could persist, forming a dense shroud. Simulations suggest this shroud might not just insulate the planet, but also circulate heat efficiently, preventing the icy fate that would otherwise await a world so far from its sun. Imagine a global weather system where hurricanes the size of continents ferry warmth from equatorial regions to the poles, smoothing out temperature extremes and keeping the ocean from freezing over. Then there's the tidal factor. Like its siblings, TRAPPIST-1F is almost certainly tidally locked, with one face permanently bathed in starlight and the other shrouded in endless night. Normally, this would create brutal contrasts, a scorching dayside and frozen nightside, but a thick atmosphere and global ocean could rewrite those rules. Currents might transport warmth from the sunlit hemisphere to the dark, creating a twilight zone where temperatures hover in a life-friendly range. And beneath the ice that could form on the night side, geothermal heat or tidal flexing might maintain liquid pockets, just as they do on moons like Europa. The most thrilling question, though, is one we can't yet answer. Does TRAPPIST-1F's ocean connect to a rocky seafloor, or is it floating atop a layer of high-pressure ice, cut off from the minerals that life on Earth depends on? If it's the former, hydrothermal vents could dot the abyss, spewing nutrients into the water, a recipe for life as we know it. If it's the latter, the ocean might need another energy source, like chemical reactions at the ice-water boundary. Either way, this world challenges our assumptions, proving that habitability isn't about mimicking Earth exactly, but about nature finding new paths to the same destination. What makes TRAPPIST-1F so extraordinary isn't just its potential to host life, it's the way it forces us to rethink the boundaries of where life can thrive. In a system where planets are stacked like cosmic peas in a pod, where gravitational tugs and shared starlight create a web of interactions, this world stands as a testament to the universe's creativity. It's a reminder that the ingredients for life might be universal, but the recipes are endlessly varied. And as we inch closer to probing its atmosphere with next-generation telescopes, we're not just searching for water or gases, we're peering into a mirror that reflects not just what's out there, but how narrow our own definitions of home might really be. Kapteyn b isn't just another exoplanet, it's a relic from the universe's youth, a time capsule world that's witnessed nearly the entire history of cosmic evolution. Orbiting a dim red dwarf just 13 light-years away, this super-Earth has existed for roughly 11 billion years, more than twice as long as our solar system. That staggering age means Kapteyn b was already 5 billion years old when Earth formed, a mind-bending perspective that reshapes how we imagine life's potential. Picture a planet that's endured through the rise and fall of countless stars, through galactic collisions and cosmic upheavals, all while maintaining its position in the habitable zone of its fading sun. What makes this ancient world so extraordinary isn't just its longevity, it's the radical implications for biology. If life took root here, it's had 5 times longer than Earth's entire history to evolve. Imagine civilizations that could have risen and fallen during epochs when Earth was still a swirling cloud of stellar debris, or perhaps single-celled organisms that slowly perfected survival strategies across geological timescales we can barely comprehend. The possibilities stretch the imagination: silicon-based lifeforms adapted to the planet's cooling core, or photosynthetic organisms that learn to harness the dimmest starlight through pigments we've never seen. Yet Kapteyn b's environment would challenge even the hardiest life. Its star, Kapteyn star, is a halo star, a wanderer born in a dwarf galaxy devoured by the Milky Way long ago. Unlike the sun's steady glow, this red dwarf emits just 4% the visible light, bathing its planet in perpetual twilight. At first glance, that seems inhospitable, but here's where planetary science gets fascinating. During Kapteyn b's youth, its star would have burned hotter and brighter. Over billions of years, as the star cooled, the planet's orbit may have gradually migrated inward, keeping it in the habitable zone through a delicate cosmic dance. This means life, if it exists, would have needed to adapt to ever-dwindling sunlight, like a civilization slowly turning down the lights over millennia. The planet's current conditions present both obstacles and opportunities. Tidal locking seems inevitable, one side forever facing the star, the other lost in eternal night. But beneath a thick atmosphere, winds might spread warmth across the terminator line, creating a twilight belt where temperatures balance just right. Alternatively, geothermal heat from radioactive decay in the planet's ancient core could maintain subsurface oceans, shielded from the star's weak light. Some models even suggest Kapteyn b could be a water world, its surface entirely covered by an ocean kept liquid through atmospheric pressure rather than stellar warmth. The most profound question Kapteyn b forces us to confront isn't just whether life exists there, but whether life could survive the unthinkable stretches of time it's endured. On Earth, evolution thrives on catastrophe. Asteroid impacts, ice ages, and volcanic winters force adaptation. But what happens on a world so stable it's barely changed for billions of years? Would life there stagnate, or would it reach complexities we can't fathom? With 13 light-years being practically next door in astronomical terms, future telescopes might one day glimpse Kapteyn b's atmosphere, searching for the chemical fingerprints of organisms that mastered survival when the universe was still young. Until then, this ancient world serves as a humbling reminder. life's story might be far older and far stranger than we ever dreamed. Kepler 2-18b doesn't just orbit in its star's habitable zone, it redefines endurance. This Earth-sized world, discovered in 2014, circles a K-type star over 1,700 light-years away, following an orbit that places it squarely in the region where liquid water could exist. What makes this planet particularly fascinating isn't just its size, just 15% larger than Earth, but the remarkable stability of its stellar parent. Unlike the violent tantrums of red dwarfs or the gradual brightening of sun-like stars, K-type stars like Kepler 2-18b offer a middle path, steady luminosity with minimal flares, creating conditions where climates might remain stable for tens of billions of years. Imagine a star slightly cooler and smaller than our Sun, glowing with a soft orange hue as it bathes its planets in gentle, consistent light. This is Kepler 2-18b's gift to its orbiting worlds, a serenity rarely found among habitable zone exoplanets. While Earth's sun will eventually swell into a red giant, rendering our planet uninhabitable, Kepler 2-18b will keep shining with barely a flicker for an almost incomprehensible span, outlasting our Milky Way's current age by multiple times. For a planet like Kepler 2-18b, this translates to an unimaginable runway for life to emerge, evolve, and potentially flourish without the existential threats posed by stellar instability. The planet's orbital rhythm adds another layer of intrigue. Completing a full revolution every 93 days, Kepler 2-18b dances at just the right distance to receive warmth without scorching, in a configuration reminiscent of Venus's position in our own solar system, but with a crucial difference. K-type stars emit less ultraviolet radiation than their hotter counterparts, meaning any potential atmosphere here wouldn't face the same relentless erosion. Early climate models suggest that with an Earth-like atmosphere, surface temperatures could hover in a comfortable range, allowing for liquid water across vast stretches of its surface. Yet the true wonder lies in the chemistry this stability enables. Over billions of years, uninterrupted by stellar tantrums or dramatic shifts in luminosity, the planet's geochemical cycles could achieve an equilibrium far more delicate than Earth. Volcanic activity might steadily replenish atmospheric gases without overwhelming them, while weathering processes could regulate carbon dioxide levels with precision. Picture a world where continents erode into seas at a glacial pace, where seasons flow into one another with barely a ripple in global temperatures, and where evolution unfolds across epochs so vast they make Earth's history seem like a fleeting moment. The unanswered questions are as compelling as the certainties. Is Kepler 2-18b tidally locked, with one face forever turned toward its star, or does it rotate freely, granting it Earth-like day-night cycles? Does it boast active plate tectonics, or has its interior cooled over the eons? Each possibility paints a different portrait of potential habitability. A rotating planet might develop diverse biomass across latitudes, while a tidally locked world could host life clustered in the twilight ring between eternal day and endless night. One thing remains clear: in the cosmic search for life, endurance matters just as much as location, and few worlds exemplify that truth like Kepler 2-18b, a planet where time itself becomes an ally in life's grand experiment. GJ 581g isn't just another exoplanet, it's a cosmic ghost story, a world that flickers in and out of scientific certainty with each new study. Discovered in 2010, orbiting a quiet red dwarf just 20 light-years away, this super-Earth sparked immediate excitement. With a mass 3 to 4 times that of our planet and an orbit squarely in the habitable zone, GJ 581g seemed tailor-made for liquid water and just maybe life. But here's where the mystery deepens. Not all astronomers agree it exists at all. The debate hinges on something deceptively simple: gravity's subtle tug. GJ 581g was detected using the radial velocity method, where scientists measure how a star wobbles as planets pull on it. But red dwarfs like GJ581 are notoriously jittery, their surfaces roiling with magnetic activity that can mimic planetary signals. Some teams analyzing the same data found no trace of the planet, arguing the wobbles could be stellar noise masquerading as a world. It's like trying to hear a whisper in a hurricane. The signal might be real, or it might be the storm playing tricks. Yet the possibility is too tantalizing to ignore. If GJ581g is real, it's a marvel of cosmic engineering. Tidally locked to its star, one side would bask in eternal crimson daylight, the other shrouded in endless night. But between these extremes lies the Terminator line, a twilight belt where temperatures might balance just right. With a thick enough atmosphere, winds could ferry warmth from day to night, weaving a narrow ribbon of habitability. Some models even suggest geothermal heat or tidal flexing might keep subsurface oceans liquid regardless of surface conditions. The real intrigue lies in what this controversy reveals about exoplanet science. GJ581g isn't just a planet, it's a test case for how we detect worlds at the edge of our technological limits. Future telescopes might settle the debate, but for now it remains a celestial riddle. And that uncertainty is its own kind of gift. Whether real or illusion, GJ581g reminds us that the universe guards its secrets closely, revealing them only when we're ready to look closer, think deeper, and question everything we thought we knew. Kepler 296e isn't just another Earth-sized exoplanet, it's a cosmic tightrope walker, balancing delicately in a gravitational dance most planets would find chaotic. Picture a world almost identical in size to our own, orbiting not one but two stars in a binary system, where the skies might hold twin suns casting ever-shifting shadows across its surface. Located about 1,100 light-years away in the constellation Lyra, this fascinating planet completes an orbit every 34 days, placing it firmly in the habitable zone of its primary star, a dim red dwarf. But here's where the plot twists. That primary isn't alone. Kepler 296e shares its cosmic neighborhood with a second, even fainter star, creating a stellar partnership that could sculpt climates unlike anything we've seen. What makes this binary arrangement so extraordinary is the interplay of light. The primary star provides most of the planet's warmth, bathing it in a perpetual crimson glow. Yet the companion star, though dim, adds subtle complications. Its gravitational tugs might periodically stretch or compress the planet's orbit, creating gentle climatic pulses over centuries. More intriguingly, during certain alignments, both stars could shine simultaneously in Kepler 296e's sky, their combined light offering brief surges of energy. Imagine seasons dictated not just by axial tilt, but by the rhythmic approach and retreat of a second sun, like a celestial metronome ticking in slow motion. Then there's the question of atmosphere. Earth-sized planets around red dwarfs often struggle to retain their air against stellar winds, but Kepler 296e might have an advantage. Some models suggest binary systems could actually protect planets. The companion star's gravity might deflect damaging radiation, acting as a cosmic shield. If true, this world could boast an atmosphere thick enough to distribute heat globally, preventing the extreme temperature swings typical of tidally locked planets. Picture swirling cloud formations racing across alien skies, driven by winds balancing warmth between the scorching day side and frigid night side. The real marvel, though, lies in the potential for complexity. On Earth, life thrives on variation. Tides, seasons, day-night cycles all drive evolution forward. Kepler 296e's dual stellar influences could offer a richer palette of rhythms. Perhaps microbial life synchronizes with the binary star's orbital dance, blooming when both suns align, then hibernating during solitary periods. Or maybe the planet's rotation, influenced by two gravitational partners, creates day lengths that vary subtly over millennia, forcing adaptability at scales we can barely fathom. This world challenges our search for habitable planets in the best possible way. It proves that stability doesn't always mean simplicity, that life might flourish not despite cosmic chaos but because of it. As we study systems like Kepler 296, we're forced to expand our definition of Earth-like, not just in size or temperature, but in its capacity to nurture complexity under alien suns. And that revelation might be the key to finding life where we least expect it. HD 69830d shatters expectations. A Neptune-sized world where gas giants aren't just cosmic neighbors but potential landlords for life. Orbiting a star eerily similar to our Sun, this behemoth defies the usual habitable zone rules. Most planets in this precious region are rocky, Earth-like worlds, but HD 69830d is nearly 11 times Earth's mass, a swirling ball of hydrogen and helium with no solid surface to speak of. Yet tucked within its turbulent atmosphere, or perhaps dancing around it in delicate orbits, could lie the real prizes. Moons so drenched in possibility they rewrite the rules of where life might thrive. Picture this, a gas giant bathed in the golden light of a sun-like star, its habitable zone stretching far enough that even distant moons could bask in warmth. Around Jupiter and Saturn, we've seen how moons like Europa and Enceladus harbor subsurface oceans despite their frozen exteriors. Now imagine that same magic amplified, a moon twice Earth's size with a thick atmosphere and sprawling liquid water seas circling HD 69830d. The ingredients are tantalizing. A massive planet's gravity could flex the moon's interior, generating heat through tidal forces, while its magnetic field might deflect deadly cosmic rays, offering a protective shield. Volcanic activity could churn nutrients into alien oceans, and with the primary star's steady energy, photosynthesis might even be possible under skies streaked with the colossal swirls of the parent planet storms. But here's the twist, this system is already a cosmic oddity. HD 69830 is famous for its massive asteroid belt, 20 times denser than our own. That means any moons here would face relentless bombardments catastrophic for life as we know it, or perhaps a delivery mechanism for water and organic compounds, seeding oceans with the building blocks of biology. It's a paradox where danger and opportunity collide. The presence of 3 Neptune-sized planets in the system only deepens the intrigue. Their gravitational interplay could have scattered asteroids inward, creating that thick belt, or maybe stabilized orbits to allow moons to exist undisturbed for billions of years. The real genius of HD 69830d lies in its duality. It forces us to consider that life might not need Earth-like planets at all. Instead, it could flourish on moons tethered to gas giants, worlds where the tides never stop shifting, where the sky is dominated by the swirling hues of a massive planet, and where the very forces that seem hostile might be the sparks that ignite biology. Future telescopes could hunt for signs of moon atmospheres, oxygen, methane, or even industrial pollutants hinting at civilizations far stranger than we've dared to imagine. Until then, this Neptune in the habitable zone stands as a monument to the universe's creativity, proving that life's playground might be vaster and far more exotic than we ever suspected. Kepler 438b teases us with Earth-like perfection, on paper at least. This exoplanet, orbiting a red dwarf star 470 light-years away, matches our home world almost exactly in size, with a radius just 12% larger. Its 235-day orbit places it snugly in the habitable zone, where sunlight is gentle enough for liquid water yet strong enough to prevent global glaciers. At first glance, it's the kind of world science fiction dreams of: a rocky planet with the right dimensions, the right distance, the right ingredients for life as we know it. But the universe loves a twist, and Kepler 438b comes in the form of its tempestuous star. Red dwarfs are notorious for their tantrums, and this one is no exception. Kepler 438 unleashes superflares, violent eruptions of radiation, up to 10 times more powerful than anything our sun produces. These aren't the gentle solar flares that paint Earth's poles with auroras. They're apocalyptic blasts capable of stripping atmospheres down to barren rock over geologic time. For a planet as close to its star as Kepler 438b, the effect would be like standing next to a nuclear detonation repeatedly for billions of years. Even the thickest atmosphere would struggle to endure that kind of punishment. Yet here's the haunting question: what if it did? Some models suggest a magnetic field stronger than Earth's could deflect the worst of the stellar onslaught, acting as an invisible shield. Or perhaps the planet's geology continuously replenishes its atmosphere through volcanic outgassing, creating a dynamic equilibrium where loss and renewal balance out. There's even speculation that life, if it existed here, might have evolved underground or underwater, using kilometers of rock or ice as a radiation bunker. Imagine entire ecosystems thriving in subterranean aquifers, their existence hidden from the deadly fireworks above, but the scars might already be visible. Observations hint that Kepler 438b's atmosphere, if it ever existed in abundance, has likely been eroded to a thin veneer. That doesn't just mean a lack of air, it means no pressure to keep water liquid on the surface. Any oceans that once sparkled under its crimson sun may now be frozen relics, locked beneath ice or boiled away into space. Yet even this grim scenario holds a flicker of hope. Mars proves that atmospheric loss isn't always total. If remnants linger, or if the planet's interior still exhales gases, there could be pockets where tenacious life clings on, a whisper of biology in a cosmic storm. Kepler 438b is a paradox, a world that ticks every box for habitability, then watches as its star scribbles over the answers. It teaches us that finding Earth's twin isn't just about size and orbit. It's about survival in a universe that doesn't play fair. And yet, against all odds, this planet refuses to be written off. Whether it's a cautionary tale or a story of resilience waiting to be told depends on what we discover next. One more mystery in the endless search for life beyond our pale blue dot. Gliese 832c isn't just another habitable zone planet, it's a cosmic pendulum, swinging between extremes with every orbit around its crimson sun. Located just 16 light-years away, this super-Earth is one of our closest potentially habitable neighbors, a world with nearly 5 times the mass of our own, yet clinging to the delicate edge of conditions that might allow life to exist. What makes this planet so captivating isn't just its size or proximity, it's the roller coaster of seasons its elliptical orbit could unleash, a rhythm of climatic upheavals that would make Earth's winters and summers feel like minor fluctuations. Imagine a year where the planet's distance from its star varies dramatically, like a carousel horse galloping closer, then retreating. At its nearest approach, Gliese 832c receives a surge of stellar energy, potentially spiking temperatures enough to thaw frozen deserts or vaporize shallow seas. Then, as it swings outward, the chill descends, locking water back into ice. These aren't the gentle seasonal shifts we know, they're planetary-scale transformations where the difference between sweltering and frigid could hinge on a few weeks of orbital geometry. For life, this would be a relentless test of adaptability, a cycle of boom and bust demanding resilience unlike anything on Earth. Yet nature has a way of finding equilibrium. The planet's super-Earth mass might be its saving grace, offering enough gravitational muscle to hold onto a thick atmosphere. A dense shroud of gases could act like a planetary shock absorber, redistributing heat during those scorching close passes and trapping warmth during the frigid stretches. Picture a world where hurricane-force winds constantly churn the air, smoothing out temperature extremes between hemispheres, or perhaps volcanic activity driven by tidal forces from the star's pull, pumps enough greenhouse gases into the sky to keep the climate stable despite the orbital chaos. The star itself adds another layer of intrigue. Gliese 832 is a red dwarf, but an unusually quiet one. No violent flares, no radiation storms. That stability is a rare gift for a planet so close, offering a chance for an atmosphere to persist over billions of years. And here's the kicker. While the star's faint glow means perpetual twilight by Earth standards, the planet's thick air could scatter and amplify that light, painting the skies in perpetual hues of orange and red, like an endless sunset over alien landscapes. But the real question is whether life could ride out these orbital extremes. On Earth, organisms thrive in places like Antarctica's dry valleys or Yellowstone's boiling springs, environments that hint at biology's tenacity. If Gliese 832c has liquid water, even intermittently, extremophiles might flourish, hibernating during the cold spells and blooming in brief, intense summers. Or perhaps the planet's oceans never fully freeze or boil, their vast thermal inertia buffering against the swings, creating refuges where life could endure uninterrupted. This world challenges our search for habitability in the best possible way. It proves that Earth-like doesn't have to mean gentle. Life might not need perfect equilibrium, just a foothold, a niche where the chaos ebbs enough for chemistry to become biology. And as we study Gliese 832c, we're forced to expand our imagination, to consider that the most alien worlds might not be the ones devoid of change, but those where life dances to rhythms we're only beginning to understand. Kepler 22b isn't just another exoplanet, it's a milestone in cosmic discovery, the first world ever confirmed by the Kepler Space Telescope to orbit snugly within its star's habitable zone. Picture a planet 2.4 times the size of Earth, circling a star strikingly similar to our Sun, with a year lasting 290 days, close enough to our own orbital rhythm to feel eerily familiar. When scientists announced its discovery in 2011, it wasn't just the dimensions that captivated imaginations. Kepler 22b offered something revolutionary, proof that Sun-like stars could host planets in that elusive Goldilocks region, where temperatures might allow liquid water to exist without boiling or freezing away. What sets this world apart is its delicate cosmic balancing act. Unlike the turbulent red dwarfs that dominate the exoplanet catalog, Kepler 22b's star is a G-type main sequence star, a near twin to our Sun in temperature and stability. That means no violent flares scorching the surface, no erratic bursts of radiation stripping away atmospheres, just the steady glow of a mature star, bathing its planet in consistent, life-friendly light for billions of years. But here's where the mystery deepens. We still don't know if Kepler 22b is a rocky super-Earth, a gaseous mini-Neptune, or something even more exotic. Its radius suggests a range of possibilities, from a waterlogged world with global oceans to a gaseous orb with no solid surface at all, the most tantalizing scenario. A true water world. If Kepler 22b's density skews lower than Earth's, it could be shrouded in a vapor-rich atmosphere overlying an ocean hundreds of miles deep. Imagine a planet with no continents, no mountains, just endless water stretching from pole to pole, churned by tides from a hidden rocky core. In such an environment, life might thrive around hydrothermal vents on the seafloor, much like Earth's extremophiles clustered in the abyssal darkness. Alternatively, if the planet retained a thick hydrogen envelope during its formation, its crushing atmospheric pressure could create oceans of supercritical fluid, where water behaves as both liquid and gas, dissolving minerals into a swirling, primordial soup. Yet the real genius of Kepler 22b lies in its legacy. Before its discovery, the habitable zone was a theoretical concept, a hopeful sketch in astronomers' notebooks. This planet turned that sketch into a roadmap, proving that Sun-like stars could indeed harbor worlds where conditions might mirror Earth's. It taught us that habitable doesn't always mean Earth-like, that life's potential might unfold in oceans without shores, under skies thick with steam, or in pressures that would crush a submarine. And while we may never know for certain what secrets this distant world holds, its greatest gift was shifting the question from, are there others like us? To how many different ways can a planet cradle life? That revelation alone makes Kepler 22b not just a scientific triumph, but a beacon in our cosmic search for neighbors. From scorching super-Earths to frozen ocean moons, the 30 worlds we've explored today prove one thing beyond doubt: the universe loves variety. Each of these distant planets tells its own extraordinary story, rewriting the rules of what we considered possible. Some, like Kepler 438b and Kepler 1638b, tease us with their Earth-like dimensions while hiding brutal stellar tantrums or mysterious compositions. Others, like K2-18b and GJ 1214b, stretch our imagination with global oceans under crushing atmospheres or beneath miles of ice. Then there are the outliers: Wolf 1061c with its wild elliptical seasons, HD 69830d with its potentially life-bearing moons, and Kapteyn b, an ancient relic that's witnessed cosmic history unfold across 11 billion years. This staggering diversity does more than catalog potential homes for life. It challenges us to rethink what habitable even means. We began our search looking for Earth twins, but the cosmos keeps handing us puzzles instead of copies. Tidal locked worlds with eternal twilight zones, planets bathed in crimson sunlight under triple star systems, super-Earths where gravity turns every step into a workout. Every discovery forces us to expand our definition of life's playground. And the most humbling realization: we've barely scratched the surface. With thousands of confirmed exoplanets and billions more waiting to be found, statistical probability suggests we're surrounded by worlds even stranger than we've dared to imagine. Yet for all we've learned, the burning question remains unanswered. Is anyone out there? Current technology lets us detect atmospheres and estimate temperatures, but spotting concrete signs of biology, oxygen spikes, methane cycles, even industrial pollutants requires tools we're only now building. The upcoming Habitable Worlds Observatory, next-generation ground-based telescopes, and advanced spectrographs promise revolutionary leaps, potentially identifying biosignatures within decades. But the real breakthrough might come from something subtler: a statistical inevitability. With each new, potentially habitable planet discovered, the odds tilt further toward life being not just possible but probable. So where does that leave us? Right where humanity has always been, at the edge of discovery, peering into the dark with a mix of wonder and determination. The search for alien life isn't just about science, it's about understanding our place in the cosmic story. Whether the next breakthrough comes from Proxima Centauri B's shadowed glaciers or TRAPPIST-1F's hypothesized global ocean, one thing's certain: we're living through the greatest detective story in history. And you've got a front row seat, so keep watching the skies, stay hungry for answers, and remember, every time we point a telescope at a distant sun, we're not just exploring planets. We're redefining what it means to be home.